All right, this week we are covering more chapter 11, which is non-parametric tests. So recall that last week we did the sign test, and the sign test was pretty straightforward, but also super basic. So if you notice, the magnitude or the amount of difference between the data values was not accounted for. It was just the plus and minus signs. The assumptions were almost nothing. We were talking about the only assumption we needed was the fact that they were randomly selected, and that's true about most non-parametric tests, excuse me, which is why non-parametric tests is not your go-to because you want to make sure that you are doing the most accurate test, and parametric tests will always be more accurate, but they are much more difficult to meet the assumptions needed to run a valid parametric test. So let's jump over to the PowerPoint. I just realized it's not at the beginning, so there we go. Okay, so 11.2, we're going to dive into two different Wilcoxon tests. The first one is the signed rank test, and the next one is the sum rank test. Neither one of these can be done in our Guru. Luckily, they're like last week, where they're fairly easy to pick up and to use, which means that we really don't need the software to do this for us. What's great is when we cover 11.3 this week, the Kruskal-Wallis test can be done in our Guru, which saves you a bit of math to calculate the test statistic. Other than that, everything else is pretty much straightforward. So the disadvantage of the sign test that we discussed last week is that it wastes information, like I said. It merely counts the number of positive and negative signs in a paired difference experiment, but it ignores the magnitude of the differences. The Wilcoxon signed rank test is a non-parametric technique which can be used to elevate a paired difference experiment. This test is designed to detect populations whose centers are shifted to the right or to the left of each other. Also, the same as when our alternative hypothesis is a left-tailed or right-tailed test. As with the sign test, no distributional assumption is required, so we don't need it to be normally distributed. However, we do need to know that the data is randomly selected. Ranking is nothing new to us. We did that last week. No, actually, I don't think we ranked anything last week. So this is something new to us. Simply put the data in order from smallest to largest and rank the lowest value as rank 1 and the highest value, your highest rank. Could be n, which is the sample size, or it might just be the highest value, the highest rank of the set. So uh, Also, just like the sign test, the zeros are ignored. So anything that has a difference of 0, you ignore them and you take them out of the count of the sample size n. How do we handle ties? Well, if there's 2 or more values with the same magnitude, these values will each be assigned the same rank, which is equal to the average of the ranks that would have been assigned to these values if they had slightly different consecutive values. So for example, if we have 3 6s in a data set, and let's say that their ranks were going to be 3, 4, and 5, we would take the ranks 3, 4, and 5, add them up and divide by 3, and then apply that rank to all 3 of those 6s. So here's a data set of an example of ranking. This one has no duplicates. So we see that the smallest value gets the rank of 1, and the highest value gets the rank of 9. Now let's see, here's rank 4 and rank 5. Let's say that 77.1 and 83.75 were both 77.1s. Then you would take 4 and add 5 to get 4 and divide by 2, get 4.5, and you would apply the rank of 4.5 to both the 4 and the 5. So to both the 77.1 and pretending that this is also 77.1, these would both be 4.5. The lowest price stock is Packard Co. at 14.23, and it was assigned rank 1. The next lowest assigned rank 2, and the highest assigned rank 9. The test procedure for the Wilcoxon signed rank test will be developed in the next example. So we have a consulting firm that implemented a quality program in an effort to improve the productivity level of its employees. All employees received 2.5 days of intensive training on the concepts of total quality management with an emphasis on process mapping. In addition to the initial training, each employee participated on a team of either quality enhancement team or continuous improvement team, which focused on either breakthrough improvements in the process or in the continuous improvement. Each team was given the responsibility and the authority to implement the improvements to the process which it deemed necessary. A year after the initial training, the management of the company conducted a study to see if the productivity level of its employees had improved. The productivity level of the employees is measured by realized billable hours per week. Realized billable hours are the number of hours which an employee works and bills to a client. 9 employees are randomly selected, and the realized billable hours are calculated before they had the training and 1 year after they had the training. The results of the survey are shown in the table on the next slide. Based on the data, can the management of the consulting firm conclude that the productivity level of its employees has significantly improved over the past year with an alpha level of 0.05? Okay, instead of going to the next slide, let me jump to an Excel file I created. So I took the chart out of the next slide and created an Excel file. Yes, I believe this one I did share with you. So this file is in the course content folder for this week, and we just want to do the work together. So if you want to pause this video if you're watching it, you might want to go into this week's content folder and grab this Excel file, especially if you do not have experience with writing formulas in Excel, so you can practice this with me. So the first column says that I need to find the differences between before minus after. So to start a formula in Excel, you type an equal sign. I will click the before, type subtraction, and click the after. Now, when you're building formulas in Excel, if I only need to write it once, and I will show you how to copy and drag the formula for the entire column. Now, when you drag a column in Excel, it does assume that you want the values in the same row as the result cell. So it will automatically drag all of these columns down these two cells, or two columns. If you ever want to write a formula where one of the values in the formula you do not want dragged, you want it to stay exactly that number, you will have to lock it in using your F4 button on a PC or Command T on a Mac. We don't have any values in this formula that we want to keep stuck, so we're good to go. We're going to hit enter. -5 is the difference between before and after. If I one click on the cell I just wrote the formula, and the formula is up here, then I can go to the bottom right of the cell until my cursor turns into a skinny black cross, click, hold, and drag in order to produce my differences for the entire row, column. Then it says, what are the absolute value of the differences? Okay, so we're going to hit equals. Absolute value, I start typing absolute value and we see, oh, that must be the command in Excel. So I double click. I click the cell to the left and hit enter. And same thing, skinny black cross, click drag. Okay, now we're going to rank these. Now the 0, we ignore. 1 is the lowest value, so we will rank that a 1. And we have a 2, which will be ranked 2. Now we have 2 3s. So one of these 3s would have been a 3, and the other 3 would have been a 4 if, let's say, the data values were 3 and 4. So we add 3 plus 4, 7. We divide by 2, and we get 3.5. So we're going to apply the ranking of 3.5 to both of 3s. Now, the next ranking would be a 5. Okay, because we already used 3 and 4, and we applied 3.5 instead. So here, our next value is 5, and there are 3 5s, and those would use up the rankings of 5, 6, and 7. So if we add 5 plus 6 plus 7, we would then divide by 3, and we'd get an average of 6. So all the data values of 5 are going to be ranked the average rank 6. And then, so we used 5, 6, and 7. So this one gets ranked an 8, the next rank. Hopefully that made sense. So another way that we could do this, take those out. Let's order these rows based on the absolute value differences. So if I go to A to Z after I've highlighted them and click smallest to largest, it's going to ask me to expand the section. You definitely want to do that because you want the ranking to correlate to the employee. So it's essentially going to move the whole row and not just the value. So we're going to sort. Okay, so this isn't going to work only because these titles, I copied them right from the PowerPoint and they are merged cells. So you can see they merged cells 1, 2, and 3 together in order to, or 2 and 3 rather, to do this. So maybe let's unmerge this one. Hold on, let me see if I can do this. I wanted to show you how to do this, but whoa. Let me just delete 3 and see if that works. All right, let's see if we can highlight, sort, expand, yes. Okay, it still won't do it, and that's because of the formatting of this cell. But normally you would be able to, it would move everything around, and then I would be able to easily apply the ranking of this, but oh well. You guys can try to figure that out. All right, let me fill these back in. These were 3.5. Then we had 3 5s, so we had 5, 6, and 7, which averaged to 6. And then there is the ranking of 8. Okay, now the signed rank column means that what was here in the original subtraction, apply that sign to the ranking. So this had a -5, which means our sign is -6. Okay, this is still ignored. -6 means that our rank becomes a -8. +3, we keep it +3.5. -5 gives us a -6. +1, +1. -5, -6. -3.5. And -2. Now what we want to do is we want to add all of the ranks that are positive and all the ranks that are negative. So our positive values, let's actually start in a new cell. Let's put equals, and we're just going to select them and add. So we have 3.5 plus 1. Those are the only 2 positive signs. Okay, and let's do the same for the negatives. So we have -6, -8. All I'm doing is selecting them and pressing plus after until I've selected all the negative ones. So Excel does a lot of the math for us, which we like. Okay, so we have our positive sum at 4.5 and our negative sum at -31.5. Let's head back to the PowerPoint. So here's the finished chart that we just came up with, and we have the same sums. Our -1, we can just we look at the absolute value of it, so it should be 31.5 positive, because essentially we compare the values, the absolute value of the magnitudes. Okay, so the first thing we want to do is determine the null and the alternative hypothesis. So the null would be that the productivity level of the employees has not improved or hasn't changed. The alternative is that it has improved. Okay, because he's only focused on one change, the improvement, not improvement or the fact that they're doing worse, we have a one-tailed test for this test. Recall that in non-parametric statistics, we do not make inferences about population parameters. The Wilcoxon signed rank test is no exception. It compares the probability distribution of the realized billable hours before the quality training to the probability distribution of the realized billable hours 1 year after the training. How is this accomplished will be discussed in step 3. Since the management is interested in knowing if the productivity level has improved, they are interested in knowing if the billable hours have increased. Thus, this is a one-sided test, as I mentioned. So the null hypothesis is the probability distributions of the realized billable hours both before and after the training are the same. And the alternative is the probability distribution for the realized billable hours after the training is shifted to the right of realized billable hours before training. We specify the alpha level at 0.05. We need to validate the assumptions of the hypothesis test, identify the appropriate test statistic, and compute its value. We must verify that the pairs of data have been selected in a random fashion and are such that the absolute value of their differences can be ranked. The data must be quantitative to assign ranking to the differences. We do know that the pairs were randomly selected because it was stated in the problem, and the billable hours are quantitative and therefore can be ranked. So this is not one of the parametric tests that can be applied to categorical data. If we let n represent the number of non-zero differences, so there was 9 data values, but one of them was a 0, which is why our n is now 8. The test statistic for the Wilcoxon signed rank test is determined in the following manner. First thing we do is compute the differences for each pair, so we did that. We rank the absolute values of the differences from lowest to highest, ignoring zeros. We calculate the positive sum, and we calculate the negative sum. The test statistic will vary depending on the sample size, the number of non-zero differences, and the alternative hypothesis. If the sample size of non-zero differences is less than or equal to 25, and the alternative hypothesis is that population X is shifted to the left or to the right of population Y, also known as a one-tailed test, use the minimum, which means the less of the two sums. So whichever one is smaller is the one that you want to use. So this is not left or right tailed test, excuse me. This is, they don't care which side you're going, and therefore it's a not equal to sign. So when you have an alternative that's a not equal to sign and you have a small sample size, you are going to use the smaller of the sum ranks. So for this particular test, which is not a two-tailed test, but if it was, we'd be using the positive sum because it came out to 4.5 versus the negative one came out to 31.5. The alternative hypothesis is that population X is shifted to the right of the population Y. Then we would use the positive sum rank associated with the positive differences, where differences are defined as observations in the population Y minus observations in population X. The test statistic is defined in this manner because we expect the number of negative differences to outnumber the number of positive ones, and thus the positive sum should have the smallest value. So we're talking about a right-tailed test here. The alternative hypothesis is the population X is shifted to the left of Y. Use the negative sum of ranks associated with negative differences, where differences are defined as observations in population Y minus X. The test statistic is defined in this manner because, again, we expect the number of positive differences to outnumber the number of negative ones, and therefore making the negative sum the smaller one. So left-tailed test pointing to the negative side of the number line, use the negative test statistic, and the right-tailed test, use the positive sum for your test statistic, and your two-tailed test, you use whichever is smaller. Okay, if you have a large sample size, bigger than 25, the test statistic can be approximated by the standard normal curve, and we would just use a Z. Okay, so Z scores are used when you have really big data sets. We are used to that, so that is not unfamiliar to us. For the example that we're working on, however, we have a very small sample size, definitely less than 25, and the alternative hypothesis is that the probability distribution for the realized billable hours after training is shifted to the right. This implies that we should be using the negative um, um, yeah, we should be no. Let's just okay. So this implies that the realized billable hours before training minus the realized billable hours after training should generally be negative. Okay, um, because we're saying that they should have more billable hours after they receive training. So if you're doing before minus after, we should expect negative differences to go coincide with what we're trying to state as our claim that after training we should see an improvement in billable hours. Okay, so that makes sense. So if the rank sum with the smallest value is the negative one, then we'll fail to reject the null hypothesis since there's no evidence that the alternative hypothesis is more reasonable. Otherwise, the test statistic is given by the positive sum of the ranks, which if you look at this one, our positive sum again was 4.5, our negative sum was 31.5. So it's looking fairly reasonable that this is following along what the claimed alternative hypothesis is. In order to calculate the test statistic, the signed ranks must be determined. To determine the signed ranks, first compute the difference, then find the absolute value, and then rank the differences using the technique that we've practiced together in the Excel sheet, ignoring zeros. Once the absolute value of the differences has been ranked, we will reassign the ranks, the sign which each associated difference had before the absolute value was computed. Finally, add all of the ranks with positive signs to determine the sum of the positive signs and add all the ranks with the negative to determine the sum of the negative signs. This procedure we've already done in Excel. Okay, so we know that since we are doing a right-tailed test, pointing to the right, pointing to the positive numbers, we are using the sum of the positives, which is 4.5. That is our test statistic. Now we need to determine the critical values, or p-value. If our sample size is small, or less than or equal to 25, the critical values are determined from a table in the appendix, which I will show you in a moment. The critical value is specified by the alpha level and the number of non-zero differences in the test, and the alternative hypothesis. Okay, so let me show you this table. So if you go into my stat lab, this is it. So if we go into my stat lab and again, we click on chapter contents, scroll all the way down to appendices, and here's all of our tables. And we click the Wilcoxon signed rank test. That will bring us to the same chart we used last week, the sign test table, but underneath it is the Wilcoxon signed rank test table. So if you notice, you have to identify whether it is a one-tailed or two-tailed test. We have a one-tailed test. We also need to know our alpha level. So my alpha level is 0.05. So I'm going to use this first column. Now, my count of data values that are non-zero differences is 8. So I'm getting that my critical value for this example is 6. Back to the PowerPoint. Okay, so we know that our critical value is 6. We know our test statistic is 4.5, which is what we just found here. So based on these specifications, the critical value determined from the table is 6. The null hypothesis will be rejected if the test statistic is less than or equal to 6. And this rejection region is displayed in the previous figure here. So if our sample size was bigger than 25, the critical values are determined in a similar manner to test statistics, which have an appropriate standard normal distribution under the null hypothesis. So essentially, you would use your inverse norm in your calculators in order to calculate critical values if we have large samples, so z-scores. All right, so making our decision, 4.5 is definitely less than 6, causing us to reject the null hypothesis. Okay, so we make a statement in conclusion. We say there is sufficient evidence for the management of the consulting firm to conclude that at an alpha level of 0.05, that realized billable hours 1 year after the quality training are significantly higher than the realized billable hours before the quality training. Okay, so summing up the procedure of the signed ranked test, the pairs of data have been selected in a random fashion, and the data is quantitative. The null hypothesis states that the populations of interest are the same. And if the alternative hypothesis is a right-tailed test, then we are subtracting y minus x. If it's two-tailed, then population x is to the right of or to the left of y. Left-tailed test, then we are doing y minus x, but x is expected to be to the left. As the right-tailed test, x is expected to be to the right. So notice x is the first set of population, while y is, or actually x represents the alternatives focus. So notice the focus for this last example we did was improvement. So that's why x had to be the after column, not the before. And then we subtracted it after. The test statistic when the sample size is small depends on the alternative hypothesis. So for a right-tailed test, we use the positive sum. For a not equal to sign or two-tailed test, we take the smaller of the two sums. And for the left-tailed test, we take the sum of the negative signs. If the sample size is big, then the test statistic needs to be calculated by that formula. So that's the only annoying formula that you're going to have to use if you do get a data set that is larger than 25. Your critical values, if your sample size is small, then you will use your table that I just showed you to find your critical value. If your sample size is large and your hypothesis is one-tailed, then you use a z-score and find it by using all of alpha. And if you have a two-tailed test, then you would use alpha divided by 2, which you should also recall that we did in chapter 6 and 7 of Stats 1. Okay, so that sums up our signed rank test. Now let's talk about the Wilcoxon rank sum test. So this is another non-parametric test. The Wilcoxon rank sum test is a non-parametric technique which can be used to compare two probability distributions when we are either unwilling or unable to make the assumptions of normality and equal variance. It may also be used in the situation where the level of the data is only ordinal. Ooh, so we're breaking it down now from fully quantitative to categorical data that can be ordered, meaning we can only rank the data. Although the Wilcoxon rank sum test does not require the assumptions of normality and equal variance for validity, it does require that two samples are drawn in a random and independent manner, and that the data must be such that it can be ranked from largest to smallest. Okay, same assumptions we're used to. Example 1. The administrator of a local hospital is attempting to control skyrocketing medical costs. A study has indicated that the longer a patient stays in the hospital, the more costly it is for both the patient and the hospital. Contrary to popular belief, the hospital suffers in these situations because it is often not able to collect the entire bill for the stay. Generally, the insurance company is unwilling to pay for the entire stay, or the individual is unwilling to pay or unable to pay. Based on the study, it appears that there are two wards with particularly lengthy hospital stays, the pediatric ward and the geriatric ward. excluding long-term care patients. It also appears that these two areas, the length of stay in the hospital is higher in the pediatric ward than in the geriatric. If there is overwhelming evidence that this is the case, all initial cost control efforts will be tested specifically at the pediatric ward. However, it could be that this observed difference is due to ordinary sampling variation, as only 10 randomly selected patient stays from each ward were observed for the study. In this case, the hospital will target its initial cost control efforts at both wards equally. Partial results of the study are presented in the table. Does the data provide for sufficient evidence for the administrator to conclude that the hospital stays are longer on the pediatric ward than the geriatric using an alpha level of 0.05? So here's the data. So we have our pediatric ward with the stay listed in days and the geriatric ward with its stay listed in days, and then the ranks have been done. So notice that here the lowest stay in days is 2 days, so that was ranked 1, and the highest stay was 60, which is ranked 20. And recall the way that we rank these. So we're looking at both of these at the same time. So even though we have two different data sets, which this is different. Sorry, I got distracted. So we are going to rank these all together. So 2 is the smallest of both the data sets, which is why it gets 1. And then the next smallest is a 3, so that gets a rank of a 2, and then a 4 gets a rank of a 3, and then 5 gets the rank of a 4, and 6 gets a rank of a 5. So it's a little harder to do because your data sets, you're ranking the original data set and not the differences. And you have to account for both of them. So notice that there were two 18s here. So they took the rank of 13 and 14 and averaged them together. And then the next up data value got the rank of 15 and so on. Okay, and then notice the next thing that they did was they summed the rank. So the ranks that were given to pediatric was 110, and the sum of the ranks awarded to the geriatric was 100. And we're really taking a look at the difference between the sums of the ranks to see if they're significantly different. So in the histograms, we indicate the length of the hospital stays appear to have a skewed distribution for each ward. Thus, the assumption of normality may not be reasonable for this data. If the assumption of normality is not met, the small sample t-test for comparing two populations would not be valid. However, independent random samples were drawn from each, and the data can be ranked, which makes it still valid for non-parametric application. So we're going to determine the null and the alternative. The null is going to represent the length of the hospital stay for the two wards is the same. We should be comfortable with that now in stats 2 that our null hypothesis is typically an equal sign saying that nothing's changed. The alternative hypothesis represents the length of the hospital stay is longer for the pediatric ward than it is for the geriatric ward. Okay, because we are not making a hypothesis about a specific population parameter, we will delay the discussion of statistical measures until step 3. Since the hospital administrator is interested in knowing if the length of stay in the pediatric is longer, that insinuates a one-tailed test. Okay, so we'll have the null be the probability distributions of the length of the hospital stay for the pediatric ward, and the geriatric ward are the same. The alternative hypothesis is stated to be the probability distribution for length of hospital stay in the pediatric ward is shifted to the right of that of the probability distribution length of the stay in the geriatric. Our alpha level is set to 0.05. We validate the assumptions, the data can be ranked, and the two samples are randomly selected and independent. The Wilcoxon rank sum test uses the idea that if the null hypothesis is true, both samples come from the same population and you should be able to combine them. After the samples are combined, notice the ranks we're using combined data, the rank of the data, and compute the sums of the rank for each. In our example, the Wilcoxon rank sum test compares the sum of the ranks, the rank sum, for pediatric ward patients to the sum of the geriatric ward patients, as I mentioned when we looked at that slide. If the null hypothesis is true, we would expect the rank sums to have approximately the same value. If the rank sums are very different, it will cause us to doubt that the observations come from the same population. Thus, the rank sum will be the measure for which we use our test statistic, for our test statistic. How large a difference in the rank sums is necessary before they are considered significantly different? This we will answer by looking at the critical values in step 4. So if our sample size is less than or equal to 10, the test statistic is given by the rank sum associated with the population from which the smallest sample is taken. Okay. Now, our samples happen to be the same size, so that's not helpful. T, the rank sum of the population with the smallest sample size, is your test statistic. If the sample sizes are equal, such as our example, use the rank sum associated with the population in the alternative hypothesis, which is specified to be shifted to the right or to the left. Okay, so we are saying that the pediatric ward is the one that's shifted to the right, and therefore we would use the 110 as our test statistic. If our sample size was bigger than 10, the test statistic is given in the procedure following this example. The distribution of the test statistic can be approximated by a standard normal distribution, the z-curve. For the hospital example, our sample size for the first one is 10, the pediatrics, and the sample size for the geriatrics is 10. Since the two sample sizes are the same, we will use the rank sum associated with the pediatric ward since it is specified to be shifted to the right of the geriatric ward, the alternative hypothesis. So, since the two sample sizes are equal, the test statistic is equal to the rank sum of the population shifted to the right, which is the pediatric, and 110. Determine the critical values. If our sample sizes is less than or equal to 10, the critical values are determined from the table for the Wilcoxon rank sum test. The critical value is specified by using the alpha level, the size of the first sample, the size of the second sample, and whether the test is one-sided or two-sided. If the alternative hypothesis is one-sided and specifies that the population X is to the right of population Y, the null hypothesis is rejected, and we would see that by using the table. Okay, if the alternative hypothesis is two-sided and specifies that the population X is either to the left of Y or to the right of Y, the null hypothesis is rejected, and we'll see that in the table. Essentially, they're just talking about the rejection zones and everything you already know. So if it sounds confusing, it's really just talking about rejection versus failing to reject. And same thing there. Okay, for the hospital example, since our sample size of the first population is 10 and the second one is also 10 and our alpha level is 0.05, and the alternative hypothesis is talking about the pediatric ward being longer than the geriatric. Thus, this is a one-sided test with length of stays in the pediatric ward hypothesized to be shifted to the right of the length of stays in geriatric. Using the table, we will find the null hypothesis should be rejected, and the rejection zone is displayed in this picture. Okay, if the sample size was bigger than 10, the critical values are determined in the usual manner we normally would, using a standard normal curve and using z-scores. Okay, so we know the test statistic is 110. Let's see how they found this critical value of 127. Now, you guys do not have the proper table for this one. It is not in my stat lab, and I don't believe I posted it either yet. So I will do that after I finish this recording. So by the time you see this, it will be posted. So I took a picture of the book, the Hawks book that this comes from, and here is the table that we would use. So we have a one-tailed table and a two-tailed table. And notice that these are very specific. So one-tailed test with 0.025, two-tailed with 0.05. Okay, here's one-tailed test for 0.05, and if you were using a 0.1, you would use this for two-tailed. So we have a one-tailed test at 0.05. Our first sample size is 10. Our second sample size is also 10. So we have, oh, okay, 10 and 10. Okay, got it. So sample size 1 is 10, sample size 2 is down, and that's 10. And here's how they get the if it was two-sided. So they have two numbers here because they're saying if it's a two-tailed test that you were looking for, you would need the lower and the upper. We're only doing a right-tailed test, which is why when you see in the PowerPoint, they said the critical value was only 127. That was because that was the right-tailed upper critical value, 127. So I will post this picture so you guys can have the chart in front of you. Okay, so the difference between the observed value and the hypothesized value cannot be attributed to anything other than ordinary sampling variation. We failed to reject the null hypothesis, and therefore we're saying that the, what were we talking about? Oh, the hospital, that the stays are not significantly longer in pediatric than they are in geriatric, that the difference in the values are simply of random chance. Okay, so there is not enough evidence for the hospital administrator to conclude at an alpha level of 0.05 that the length of the hospital stays in the pediatric ward is longer than the geriatric. The hospital should direct the control efforts of their cost at both of the wards. Assumptions are that the data has to be able to be ranked and that the two samples are independent and randomly selected. The null hypothesis is always going to be set to the probability distributions of the two populations of interest are the same, while the alternative can be one-tailed or two-tailed. Okay, the first size of the sample is the smaller of the sample sizes, and the second one will be the larger if they're different. If we have a sample size that is small, less than or equal to 10, then the alternative hypothesis is right-tailed. We would follow these rules for finding our test statistic. And if it is two-tailed, we'd follow these ones, and left-tailed. So I'll have you guys read those on your own. If we have a larger sample size, then we have our test statistic calculated by this particular formula. Not difficult, annoying, but not difficult. It's the only calculation you have to do, which is why we don't necessarily need our guru to do these sections for us. I'm excited to show you 11.3 in our next video because we can use our guru for the Kruskal-Wallis test. Critical values are found as follow in this summary. So those slides are really helpful for when you are trying to go back and sum up what it is you just learned. If you go to those end slides of those tests, then you would be able to kind of create a chart that would be really helpful for you to follow when you are taking an exam on this stuff. Okay, so that concludes 11.2. I'll see you in the next video for 11.3.